Welcome to our video on data storage. We will explore the fundamental concepts of how computers represent and manage information, covering bits, Boolean logic, logic gates, and hexadecimal notation. This video delves into bits and Boolean logic, explaining how physical electronic systems are used to capture and process abstract data representations. All computer information is stored as patterns of ones and zeros, known as bits. Bits have no intrinsic numeric value. Their meaning depends entirely on the context and the rules applied to them. Boolean operations are core to computing. The AND operation requires both inputs to be 1, while the OR operation requires at least 1. The XOR operation returns 1 only when inputs differ. The NOT operation is unary, inverting a single input. Logic gates are physical devices, typically using transistors, that translate voltage levels, high for true and low for false, into these Boolean operations. Flip-flop circuits are the foundation of computer memory. They are bistatable, meaning they can retain a single state of 0 or 1 indefinitely until a pulse changes it, typically using feedback loops. Next, we will look at hexadecimal notation, a useful shorthand that simplifies long binary streams to make them easier for humans to read. Working with long binary strings is prone to errors. By grouping bits into blocks of 4, we can map them directly to a single hexadecimal character, significantly improving readability. These questions and exercises will help you practice circuit output challenges, state event tracing, understanding clock systems, and exploring compound logic. In this section, we move into the fundamentals of data storage, specifically exploring memory architecture and information encoding. We now examine the architecture of primary storage, focusing on the organization of main memory within a computer system. Memory is organized into cells, usually holding a bit, which are grouped into bytes. It follows a logical sequence, defined by high-order and low-order ends for consistent data interpretation. Each memory cell is assigned a unique numerical address, enabling random access. This system allows the CPU to read or write to specific locations, creating a comprehensive memory map. Random access memory, or RAM, allows independent access to cells. Modern systems use SDRAM for high-speed synchronization, though it remains volatile, meaning it requires power to retain data. Finally, we compare memory standards. The industry often uses metric prefixes like giga or tera for binary values, which can lead to common discrepancies in reported storage capacity. Moving on to mass storage, we will look at permanent, non-volatile storage systems that act as secondary storage for your computer's data. Magnetic disks, such as hard disk drives, use rotating platters with magnetic coatings to store bits. A mechanical arm with a read/write head moves across these spinning disks to access tracks, sectors, and cylinders. Key performance metrics for these disks include seek time, the time to move the head to a track, latency, the time for the sector to rotate to the head, and overall transfer rate. Magnetic tape offers high capacity and is cost-effective for large datasets, though it provides sequential access, making it primarily useful for archival offline storage. Optical systems like CDs use lasers to read pits on a surface. Meanwhile, flash memory, found in SSDs and USB drives, is replacing magnetic drives due to its speed and efficiency. This concludes our review of data storage and memory, covering everything from bit logic and RAM types to various mass storage technologies. We will now begin the first chapter on advanced data representation and mass systems, starting with how data is encoded and stored. Optical storage relies on pits and lands. Microscopic indentations are burned onto the disk, and the transition between these pits and the flatlands allows the system to detect binary data. Unlike disks with concentric tracks, CDs use a single spiral track. They also employ constant linear velocity, adjusting the rotation speed as the laser moves outward to maintain a consistent transfer rate. Flash memory and SSDs offer non-volatile storage by trapping electrons in chambers. Their solid-state nature provides high durability, low power consumption, and speed comparable to RAM. This chart illustrates the data organization hierarchy, showing how different levels of storage interact within a computer system. Physical blocking is essential because hardware sectors rarely match software data sizes. The OS manages this by grouping multiple logical records into a single physical record block. I/O buffers are critical for bridging the performance gap between fast CPUs and slow mechanical storage, allowing the system to continue working while I/O operations finish. For text, we use standards like ASCII. The original 7-bit ASCII supports 128 characters, while 8-bit extended ASCII allows for 256. However, these are insufficient for global languages. Symbolic representation has evolved from early history to modern digital mapping. Today, the Unicode era provides 16 to 32-bit systems that support over 140,000 characters globally. Let's explore binary efficiency regarding numbers. Representing numeric values directly in binary notation is significantly more storage efficient than encoding them as strings of digit characters. Next, we contrast bitmap and vector graphics. Bitmaps store images as a collection of pixels, which can lead to pixelation when scaled. Conversely, vector graphics use mathematical descriptions, ensuring they remain perfectly sharp at any size. Representing information requires robust bit patterns. These patterns serve as the foundational building blocks for all digital systems and data structures. Global standards and color systems are essential for universal interoperability. By standardizing how data is represented, systems across the world can communicate accurately. The International Organization for Standardization, or ISO, is a global federation that develops industrial and technological standards. The name itself comes from the Greek isos, meaning equal, reflecting its role in creating uniform global benchmarks. Digital color models vary by application. The RGB model uses additive color for screen displays, while YUV separates brightness from color to improve efficiency and maintain compatibility in video transmission. In professional design and UI development, vector graphics are favored because they remain sharp at any scale, unlike raster bitmaps, which lose quality when enlarged. Modern typography relies on resolution independence. Standards like TrueType and PostScript allow fonts to render perfectly at any size using vector outlines instead of fixed pixel grids. To digitize sound, we use sampling, taking snapshots of analog waves. Higher sampling rates, such as 44.1 kHz for CD quality, provide much better fidelity compared to telephony standards. MIDI is a highly efficient way to store music. Instead of raw audio data, it records digital instructions, like notes and timing, that a synthesizer then interprets to generate sound. The binary system is the backbone of all these technologies, providing the universal language for computers to process complex information. That concludes our module on information representation. Thank you for your engagement as we explored these essential digital frontiers.